Hi, welcome to topic B5 Current and Circuits. This is quite a long video tutorial, so please don't be put off by it. I tend to go into these concepts a little bit deeper and start from the very beginning because some of them can be quite abstract. It's important we understand two terms very clearly in our minds. The first term is electromotive force, EMF. Now, if we imagine a circuit, what we have here is a cell, and electrons then travel around the circuit. What this cell does is it gives each electron or each unit of charge a certain amount of electric energy. And you can imagine these electrons carrying this energy around the circuit. At any stage in the circuit where an electron or charge is given energy, that is known as an EMF. And in fact, the definition of an EMF, electromotive force, is when the charges gain electrical energy from a power supply. And it's defined as the energy transfer per unit charge. So E, or EMF, is equal to energy given per unit charge. And it's got units of volts. The potential difference is also a voltage, but you can imagine that once these electrons, or once this charge is given energy, it deposits its energy, or it uses up its energy at this stage here and travels back to the battery to get more energy again. So instead of gaining energy, which it happens here, it loses energy. And this is known as potential difference. And in fact, the definition of potential difference is potential difference V is when the charge loses electrical energy to a component. It's also defined as the energy transfer per unit charge, and it has the formula V equals E over Q. It also has units of volts. So let's get your revision note template out and start with an easy one. Write down the definitions of EMF and potential difference in your revision note template. So the next learning objective is about electric current, and it's known that the charge carriers within a metal are electrons, but they may be ions within other materials. We think of electric current as electrons flowing around a wire, and we're correct. But electric current is not just about electrons. It's basically a flow of charge carriers. And those charge carriers vary depending on what material you're looking at. So if we take, for example, below me, you can see a solution. There's positive ions and negative ions in that solution. If we pop a cathode and an anode in that solution and turn on the power, the positive ions are going to be attracted to the anode, and the negative ions are going to be attracted to the cathode. They're not electrons, they're just positive and negative ions. But by doing that, by being attracted to those cathodes and anodes, there's a flow of charge. An electric current is defined as a flow of charge. So when you're looking at an electrolyte or a solution, then the current is a flow of charge, and it's usually ions. If we then go to a solid like metal, the charge carriers are electron. They flow the charge around the circuit. So an electric current there is a flow of charge, and it happens to be electrons that carry that circuit round, that current round. The total charge on charge carriers is quantized based on the elementary charge. So there's no value of charge that can be smaller than the charge on an electron, which is 1.6 times 10 to the minus 19 coulombs. So any value of charge in the whole world must be a multiple of that number. And that's what quantized means. You can't just have any old number of coulombs as a charge. It has to be a multiple of this basic element of charge, E. So the charge on any ion in an electrolyte below would be an integer multiple of E. So it would be 1E, 2E, 3E, 4E, 5E, 700E, whatever. And electrons in a solid all carry the same negative electron charge, and that is minus E. So every electron carries that 1e charge, but it's a minus value. Free electrons are the charge carriers, and I can't say charge carriers. Try again. Free electrons are the charge carriers in a metal conductor, and they move randomly at high speeds. So these little electrons, you can see, you can imagine, right? They're tiny, okay? Imagine yourself at a concert, and you are the size of an ant. And everyone at the concert is normal size, and they're like dancing about, and you are trying to get past them all. That's what an electron does. It darts back and forth, trying to get past these massive other molecules, like copper molecules or whatever the wire is made out of. And they move randomly, darting about at very high speeds. But actually, as a collective body, they drift in one direction. And that's what the electric current is. But that drift, as they drift toward, because they're all negative and they drift towards the positive terminal, that drift is very, very slow. So meanwhile, inside there, they're all going like this, starting about at very high speeds. The whole body is drifting along at a slow speed. And you'd be surprised how slowly that speed is. I'll reveal it in a moment. But as we're talking about electric current as a rate of flow of charge, we need to start to bring in this term rate and how it relates to time. Because whenever you see the word rate, like rate of energy or rate of flow of charge, you need to divide it by time. So we looked at the flow of charge, we now need to divide that by time to recognise current. So electric current is the amount of charge that moves through the cross-sectional area of a wire per unit time. Would I memorise that definition? No, I'd probably memorise the definition above at the top that says current is the rate of flow of charge. It's easier and it means the same thing. Okay, so I've told you 3 or 4 definitions to memorise so far. This one, make it easy for yourself. Electric current is the rate of flow of charge. Boom, job done. Okay? Electric current is defined as the rate of flow of charge. We're looking at the rate of change, and what we define I as current is the change in charge divided by the change in time. So that's why we've got those 2 delta signs on there. It's to do with the rate of flow. Charge is a scalar. Time is a scalar, so it makes natural sense that current would be a scalar as well. The unit of current is the ampere, and I don't think that's a surprise to anybody. And the ampere is a fundamental SI unit, which is important that you know that. 1 amp could also be expressed as 1 coulomb per second, because if you look at the formula here, we've got coulombs or charge over time, so coulombs over seconds. So you could say that 1 amp is equivalent to 1 coulomb per second. Great, now we have a concept of current in our head. Let's write down the definition of current as a rate of flow of charge. Let's write down the formula for current as I equals the change in Q over the change in T. Go to your common diagram section and draw the solution with the ions flowing around it to demonstrate current, and complete questions 1 to 3 in B5 knowledge questions. We're now going to look at something called static electricity. We're going to look at its effect in everyday life and how it's produced. Let's start at the very basics. If we look at the representation of an atom here, you'll notice that we have negative charge that resides on electrons. These are the little electrons here, the green things. The electrons are much lighter than the things in the middle. And the things in the middle are nucleons. Nucleons, i.e. things that are in the nucleus. It's either protons or neutrons. And in this case, I'm really only interested in the protons. They reside inside the nucleus, and they are very heavy in comparison to the electrons. The electrons are much lighter and they're easier to move. So when we're looking at solids and we're looking at the movement of charge, it makes sense that the electrons are the ones that are going to be added or taken away from atoms and that move across the solid, because they've got less ties holding them in. Whereas the protons or positive ions are really held quite tightly inside this nucleus, and it makes it difficult for them to move. So when we rub a surface, and we have two objects here, a polythene rod and a cloth of silk, when we rub those two together, what happens is frictional forces start coming into play. And those frictional forces between the cloth and the rod, it removes the electrons from the silk. And because those electrons can freely move, they move onto the polythene rod. And what that means is there's less electrons on the silk, and there's more electrons on the polythene rod. So the silk becomes positively charged, and the polythene rod becomes negatively charged. And that's all due to frictional forces causing the electrons to move from one point to another. The types of materials that will allow this to happen are categorized into three different sections. Conductors. Conductors are materials with many free electrons which can flow easily, and a good conductor is a metal, and we'll have seen that when we studied just electrical circuits. Insulators are materials that have very few free electrons and cannot easily flow, and we're looking here at plastic, glass and wood. And semiconductors are materials that will insulate when pure, but will conduct when an impurity is added in, so in response to heat or light. And we're looking at things like silicone and germanium for that. Okay, let's head to your revision note template and take some time to write down the difference between conductors, insulators and semiconductors, but do that in terms of what we've just talked about, the mobility of charges, which ones are moving, which ones are not. This new specification doesn't give any required practicals, but in my mind, this is a required practical. There are characteristics of three components that you need to know in this specification. And these three components are a metal wire at a constant temperature, a filament lamp, and a diode. And what we want to know about these components is, how does the current vary as the voltage varies? And we call these characteristics, we call it the IV characteristics. And we ultimately end up plotting a graph for each component showing how the current varies with voltage. And it's done in a very common practical that you probably would have done in school. So I'm going to walk you through the practical now, and I'm going to walk you through what these characteristics look like for each of these three components. So we've got our source here, which is a variable power supply. And you know the kind I mean, the ones you get in your lab and you plug them in and you can put them to any value you like. But you could equally have a cell or a battery here as well. We have connectors, which are our wires, and we call them 4mm wires. And that's to do with the size of their connections at the end. We have an ammeter in series with the circuit. That means it's inside the big loop. And then we have our component, and this component here is either the filament bulb, the fixed resistor, or the diode. And we have our voltmeter, which measures the potential difference across the component, and that piggybacks over the component. And finally, we have our variable resistor. And you can see, apart from the voltmeter, they're all in one series circuit. And what we do is we set this circuit up and we insert the component we're going to investigate. So for example, we'll start with fixed resistor number 1. So where it says component, we'll pop in our fixed resistor. Then we'll vary the potential difference across the component by adjusting the variable resistor. And we'll set up a table. And our table will look like this. And we'll have voltage on this side, or potential difference on this side, and current on that side. And we'll write down what the voltage is and what the associated current is. And we'll have 6 different values, at least 6 different values for our table. And then what we'll do is we'll swap the power supply round. So instead of having a plus here and a minus here, we'll swap the power supply around so we have a minus here and a plus there. And why would we do that? Well, we do that so that when we plot our graph, we have a positive side of the graph and a negative side of the graph. And what this quadrant graph really means is on this side and this bit here, the resistor is fixed to the source the other way around. That's all that means when we have that negative side of the graph. When we look at the fixed resistor and we plot our table out into the graph, what we notice is there is a straight line through the origin. That is our characteristic of the graph of a fixed resistor. You could say that V is proportional to I because it's a straight line through the origin. And what this becomes an example of is something called Ohm's law, which we met previously, V equals IR. This says that V is proportional to I as long as resistance is constant. And this only happens in a fixed resistor when the temperature is constant as well. So this graph here is the graph you need to remember for a fixed resistor. The IV characteristics are a straight line through the origin, which shows that resistance is constant and that V is proportional to I. It's an example of an ohmic conductor. This graph is going to be really important to you, and that's all you need to remember about that. And in a moment, we'll get to the common graph section of our revision notes and we'll pop that in. A filament bulb. If we just chat a little bit about a filament bulb. A filament bulb looks like these that are shown on the screen. And they've got a filament in them. And this is a high resistance wire. And when you put current through this high resistance wire, it heats up and it causes heat and light to be emitted. If we look at this close up down here, when something heats up, these are little copper atoms, these green things. These copper atoms, when they heat up, they're going to vibrate around their equilibrium. And the hotter they get, the more they vibrate. They vibrate wildly. Now, could you imagine if you're a lonely little electron trying to get past, trying to carry the charge as a current, and these atoms are vibrating wildly? Well, it'd be super difficult, wouldn't it? So that means that when the temperature of a wire increases, the resistance to current increases as well. And that has a significant effect on what the IV characteristic graph of a filament bulb looks like. And let's go to that graph now. This is what the IV characteristic graph of a filament bulb looks like. You can see it's kind of an S shape. It does not follow Ohm's law. That's because V is not proportional to I. It's not a nice straight line through the origin. And if it doesn't follow Ohm's law, it means it's not an ohmic conductor. In fact, it's a non-ohmic conductor. And if we consider some values here, let's say that at this stage, V is equal to 2, and let's say I is equal to 3, right? And at this stage here, let's say V is equal to 4, and I is equal to, not quite as big as that, is it? It's not quite as double, so 5. Then you can see that 2 over 3 is 0.66 and 4 over 5 is 0.8. That signifies
the resistance, because R equals V over I. And as you take values up this S, you can see that the resistance increases of a filament bulb as you increase the current and the voltage. So a characteristic of a filament bulb that's shown by the IV characteristic graph is that the resistance increases as the current increases, and that is due to the increased heat of a filament wire. The final component that we need to be very comfortable with is the diode. This is the basic symbol for a diode. You might also see it like this. Circle around it. And if it's a light emitting diode, you'll see it like this with two arrows going out of it, and that signifies the light being emitted. One of the key symbols of this diode is this straight line here. I always use that to remind myself that current is blocked in one direction. And let's have a think what that means. Let's look at the graph for a diode. I, current, voltage, characteristic graph looks like this. Can you see the green line? You can see here that, let's take a value here. Let's say V at this stage is, say, V is equal to minus 10. And I is equal to 0. R is equal to V over I, which is minus 10 divided by 0. A number divided by 0 is infinity. So in one direction, for a diode, it has infinite resistance. The characteristic graph shows that when it's wired up in one direction, the resistance of a diode is infinite, and that means that no current flows. So a diode can only allow current in one direction. Let's have a look on this side now. You can see at this point here, until what we call the threshold voltage, it also has infinite resistance. It's a value of V divided by 0. But we get to the threshold voltage, and what happens is suddenly that resistance goes to 0 ohms. Current can very, very easily flow through that point. So on the other side of the diode, when it's connected up the right way, the resistance quickly changes to 0 in the other direction and current can flow. We can see that V is not proportional to I, so it does not follow Ohm's law, and it is a non-ohmic conductor. That's us flown through the IV characteristic graphs of the fixed resistor, the filament bulb, and the diode. And what I'd like you to do is go to your revision notes. I'd like you to draw your IV characteristic graphs for each fixed resistor at a constant temperature. And I'd like you to just annotate it. So resistance is constant, V is proportional to I, and it's ohmic. And then do your filament bulb, so your S shape, I, A, V, V, and this is a filament bulb. You know the score. You go and fill out this part of your revision notes in the common graph. I would like to see a graph for each of the 3 components with a little bit of annotation as to what happens to the resistance and whether it's an ohmic or a non-ohmic conductor. You've heard me using the phrase ohmic and non-ohmic conductors when we were talking about these components. It's important for you to understand that the term ohmic conductor comes from Ohm's law. And you don't really know Ohm's law yet, so let's go on and have a look at it. Let's think about current. And we've got a very funny little diagram here. What this part of the diagram is supposed to represent is a component. So, for example, a bulb. You can see that there's a figure pulling that rope tighter around the component. And it's making it very tricky for the current to get through, our green figure to get through. And that's exactly what resistance is. If you increase resistance, it makes it trickier for the current to get through, and the current decreases. But what does the potential difference do? What does the energy and the voltage do? Well, the voltage helps push the current through the component. And the greater that push is, the greater the voltage is, so if we increase our potential difference, then the more chance that the current has to get through. So if we increase the potential difference, I'm going to write PD for potential difference, and then that means we increase current because it gives it a greater push. You might even say that V is proportional to I, so that means as V increases, I increases. And that certainly seems to be the case. And those two relationships that have been observed were identified by George Ohm, who is a German scientist, and he came up with Ohm's law. And Ohm's law is otherwise known to you as V equals IR. And it's really important that you're able to use this formula. V stands for potential difference or voltage. You use those terms interchangeably. You might sometimes see it as potential difference. You might sometimes see it as voltage. And it has units of volts. I stands for current, and it has units of amperes. And R stands for resistance, which has units of ohms, which is the Greek sign for omega. Practice drawing that if you like. You need to know this formula and you need to remember the units for it. Please, can I just note that it is not acceptable to write V equals A like that. That is not your formula, okay? That is your units. You cannot write a formula in terms of units. Your formula should always be V equals IR. It's time for you to head to your revision note template and write down in the definitions section the definition of resistance as R equals V over I is one of the very few definitions that's actually defined using a formula. So your resistance is defined as R equals voltage over current. Go to your definition section again and write down the definition of Ohm's law. And then finally go to your knowledge questions that you can find below and complete questions 4 to 7. I'm bringing one of the final learning objectives in this topic forward a bit. I feel like it fits in better here. We've just talked about how current and voltage varies with 3 components. We've got our metal at a constant wire, our filament bulb, and an LED, which is a light emitting diode. We also looked at the concept of resistance and how resistance is defined as voltage divided by current. I'd like to look at 2 further components here. I'd like to look at thermistors and light-dependent resistors. LDR is a light-dependent resistor. Please don't get it mixed up with an LED. It's a different thing. And these components change the way they act depending on their resistance. So we're going to dive into these right now. Moving on to the heating effects of current, because I'm sure you've touched an electrical wire before and thought, oosh, that's hot. Okay, and it is hot, and there's a reason for that. Because if you imagine what current actually is, it's free electrons. And those free electrons are travelling between the metal ions. And in a copper wire, it would be copper ions. Okay, or copper atoms. As these electrons push past the ions of the copper atoms, they cause them to vibrate. And when an atom or a particle has kinetic energy, it heats up. So placing a current through a wire causes it to heat up. And you can see that when you look at a light bulb, because a light bulb is basically a wire, a nichrome wire this is, and it's got really high resistance, which means that the electrons are bashing about those copper atoms or the nichrome atoms loads, which means it heats up. And in fact, it heats up so much that it lights up, it glows. And that's how an old-fashioned light bulb work. But the exact opposite happens in these wires. These wires are made of copper. The electrons go through them, but it's got a low resistance, which means that the electrons flow through easier. So whilst these copper atoms do vibrate, just not as much as those in the nichrome. So it doesn't get as hot and it doesn't light up. We can use this for great stuff. How do you think your toaster works? Your toaster has a current flowing through a high resistance wire. That high resistance wire heats up and lights up. How do you think an electric fire works? A current goes through a high resistance wire. The high resistance wire heats up and lights up. How do you think your hairdryer works? A current goes through a high resistance wire. The high resistance wire heats up and a fan blows it out. Older light bulbs. Here we go. A current goes through a high resistance wire. The high resistance wire heats up and lights up. A grill. Here we go. A current goes through a high resistance wire. The high resistance wire heats up and lights up. And finally, the iron. A current goes through a high resistance wire and the iron heats up and allows you to have a nice ironed shirt. We're now going to look at a different component, and this component is a thermistor. And our learning objective says we have to be able to explain the characteristics and uses of our thermistor. Let's get on that straight away. There is a suggested practical for a thermistor, and basically what this practical does is it takes the thermistor, which is a small green thing, pops it in some water and attaches the thermistor to something called an ohmmeter. You can take your common multimeter in your class and you can pop it to the ohms setting, and you can actually attach it to any object and it'll tell you what the resistance of that object is. Now, if we pop the thermistor into this hot water and we gradually increase the temperature of the water, we can find out what the value of temperature of the thermistor is and the associated resistance of the temperature. And what we would do is we'd have a table like this, and we'd have temperature on this side, and we'd have resistance on this side, and we'd change the temperature. So let's say we start off at 10 degrees and then 20 and then 30, and we'd write down the associated temperature as we went along. So we'd increase the temperature and measure the resistance as we went along. And what we'd find is we'd plot a graph. We'd have temperature on the x-axis because that's the variable we're changing, and we'd have resistance on the y-axis, and our graph would look like our graph would be inversely proportional. That means as temperature increases, it is inversely proportional to resistance. As temperature increases, the resistance of the thermistor decreases. Before we talk about the uses of a thermistor, I'd just like to remind you the circuit symbol of the thermistor. You can see here that it's a very clear resistor underneath, which is your square box. Then the diagonal line means to vary, and this little bit here is the thermistor end of it. So a thermistor is basically a resistor with a variable component on it to show it is a thermistor. Now, the uses of a thermistor. Basically, any object that relies on the temperature varying. So if you imagine your house, you might have a thermostat and you only want your heating to go on a certain temperature. Well, there would be a thermistor inside your thermostat. If you are driving the car and you need to know the temperature outside, because maybe it's of freezing temperature, then you would find a thermistor in your car dashboard. And a fire alarm. A fire alarm works with two sensors. It works with a smoke sensor and it works with a heat sensor. So your fire alarm will have a thermistor in it as well. If we go to our revision notes, we want to include this learning objective in our revision notes, and I think we should go to the common graph section. We should plot our graph, temperature, degrees Celsius, resistance in ohms. Remind ourselves that this is a thermistor. And then I'd put three uses. Thermostat, car dashboard, and fire alarm. Job done. We have one further component that we need to be able to explain the characteristics and uses of, and this is of an LDR, which stands for light dependent resistor. So it's a resistor that varies depending on how much light is incident on it. Let's have a look. Wow, wait a minute, I recognise this graph. It looks exactly the same as a thermistor. The only thing that's different is on a thermistor on the x-axis we had temperature, and on the x-axis for an LDR we have light. And what it shows is for a light-dependent resistor, as light intensity increases, the resistance decreases. It's exactly the same relationship we saw with a thermistor. The light intensity is inversely proportional to resistance. Let's have a little look at the circuit symbol. Well, we have the resistor element to it, this box, and we have a varied amount of light, so we have a diagonal lines, and these little arrows show light entering the resistor. So a light-dependent resistor. Where would we find a light-dependent resistor? Well, it's any circuit or any system that relies on something switching on or off depending on the amount of light. So a security light, you might want a light to go on when it gets dark. But as it gets to a certain amount of darkness, a security light would switch on. Similarly, with street lights in your street, they are all working through the use of an LDR. And interestingly, a digital camera uses an LDR, because what the LDR does is it measures the amount of light that enters through the lens, and it calculates the size of the flash to use to make sure you get the best picture on your camera. So a digital camera has an LDR inside it as well. When it comes to the revision notes, it's going to be very similar to our thermistor. We're going to pop resistance up here. Light. You don't need to know the units of light, but it is lux. Our inversely proportional graph. Let's remind ourselves that's an LDR, and then let's put some uses. So digital camera and security light, just to remind ourselves. We are done. So far in this topic we've looked at a lot of concepts, but I've really only introduced 2 equations to you, and you'll notice in the data booklet there are loads more equations. Okay, so the next part of this tutorial is just really looking at the equations you might expect to use when solving current and circuit problems. The energy equation 1 is E equals PT. E equals P times T, or PET as I remember it, so PET like that, and it sort of links to this triangle here. You have to remember it correctly, because if you remember it like this, then it's obviously wrong. Don't remember that. Remember it in the right form. Energy equals power times time. Energy has units of joules, and it's a little j. Power has units of watts, and time has units of seconds. It is worth noting that you might sometimes see energy denoted as W, and the reason we might see that is because work done, which is our W, is equal to energy transferred. So you might see W equals PT, but more likely for it to be E. The second energy equation is E equals QV. Let's go back to the first one. You can see the first equation, you can find out the energy in an electrical appliance if you know the power and the time of the electrical appliance. But you might not know the power, or you might not know how long it's been applied for. So if you've got other information, like if you know the charge of the appliance, or the voltage of the appliance, or the potential difference of the appliance, you can find the energy in a different way. And the equation is E equals QV. E again stands for energy as units of joules. You might see W at this stage, so it would be W equals QV. It means the same thing. Like I said before, it's work done is equal to energy transferred. Q stands for charge, has units of coulombs, and V stands for potential difference, which has units of volts. Power equation 1. PIV. P equals IV. You can find out what the power of an appliance is if you know the current and you know the voltage. Potential difference is our V and it has units of volts. Current is our I and it has units of amperes. And power is our P and it has units of watts. The second power equation is, say you have some information about an appliance but you don't know what the voltage is. Well, you can't use PIV to find the power if you don't know what the voltage is. But you might know the resistance. So instead of using PIV, you'd use our second power equation, which is P equals I squared R. We know what P is, we've just talked about that. That's power and has units of watts. We know what current is. We've just talked about that. That's current and it has units of amperes. R is resistance and has units of ohms. First of all, the four things inside this equation are time. And as always, that is given in seconds. Potential difference. Potential difference is a fancy but the correct word for voltage. It has units of volts. Current, which has units of amperes or amps, as we mostly say, and energy, E, which has units of joules. As I said before, this equation here is the one you need to memorise, but it actually comes from the equation for power, P equals IV, and that's the equation for power you'd use in an electrical circuit. Do you also remember that PET, power equals energy over time, which means that energy equals power times time. And instead of power in there, let's put IV in there because power equals IV. So E equals IVT. That's where this equation comes from. This equation for energy is only for electrical circuits. Well, that's obvious when we can't find the voltage of a person, can't we? We can't find the current of a tree. So this equation here is to find out the energy of an electrical appliance. E equals IVT. If you're uncomfortable rearranging it, you can use this rearranging triangle here. Just as a little warning, the examiner boards don't really love these equation triangles. No idea why, but that's just their prerogative, I suppose. So if you wanted to find V, you'd place your finger over V, and what you'd see is you'd have E divided by IT. We've gone through a number of equations that will allow you to analyse electric circuits. It's now time to put some of that into practice. I put some easy knowledge questions below, and they are questions 8 to 13. We'll start with them and then we'll see in step 2, activate the application, how they are then integrated into exam style questions. This next learning objective is something that a lot of students seem to struggle with, so I'm going to really break it down into the simplest terms possible. The learning objective is to describe the difference between parallel and series circuits. Let's start with a series circuit because that's super simple. So there are 3 things that we want to identify inside a series circuit and find out what the rules are. The first element about a series circuit that I'm interested in is the current. What's the rule for the current inside a series circuit? Well, let's suggest that we took an ammeter and measured the current there. Let's say it was 2 amps. And we took an ammeter and we measured current here. It's I2. That would also be 2 amps. Let's say we took an ammeter and measured the current here. That would also be 2 amps. No matter where you measure current on a series circuit, it's always the same. So the first rule of a series circuit to do with current is that current is the same everywhere. We're now going to look at resistance. The total resistance of the circuit is a simple sum of the resistors within the circuit. So let's say that R1 is equal to 10 ohms and R2 is equal to 20 ohms. Then the total resistance, so our second rule, RT is equal to R1 plus R2. So in this case, the total resistance would be a really simple sum of 10 plus 20, which is 30 ohms. If we increase the resistance inside a series circuit, what that has the effect of doing is reducing the current. It makes it harder for the current to go through. The final quantity that we're interested in is potential difference or voltage. You might use the term voltage. I would say the sort of technically correct term is potential difference, but it doesn't really matter. And the rule for potential difference is that the potential difference across each component adds up to the total voltage supplied by the cell. So if this was 9 volts, then the voltage across this plus the voltage across this has to add up to 9 volts. Now in this case, this would be 6 volts, and that would be 3 volts, and I will explain that to you in a moment. But VT is equal to V1 plus V2. These three rules here make up our rules of a series circuit. Whenever you're dealing with questions to do with series circuits and you have to calculate the resistance or the voltage across a resistor and so on, you can always use Ohm's law. Please always do bear this in mind. But there's also a handy little ratio that you can remember. And basically what the ratio is that the potential difference, this value up here, is shared out between the components based on the resistance of each component. So if this resistor here, R2, is 3 times the size of resistor 1, then it receives 3 times the voltage share of resistor 1. And let me give you an example of that. Let's say the total voltage given out by the cell is 8 volts. Well, this, R2, would receive 3 times more voltage than R1 because it's got 3 times more resistance than R1. So V2 would be 6 volts and V1 would be 2 volts. And we can see that 6 plus 2 equals 8, but we can also see that V2 is 3 times more than V1. I'll give you another example. Let's get rid of these numbers. Let's say that R1 is 5 ohms and R2 is 25 ohms. And let's say, for example, that VT, power supply, is 12 volts. Well, R2 is 5 times bigger than R1, which means the voltage across R2 has to be 5 times bigger than the voltage across R1. So if we say that the voltage across this is 10 volts and the voltage across this is 2 volts, 10 plus 2 is equal to 12, so that adds up. But also 10 is 5 times greater than 2. It becomes a bit easier to do problems if you do consider with a series circuit the ratio of sizes of resistance equals the ratio of sizes of voltage, and that makes things a little bit easier for you to work through. Let's now have a look at a parallel circuit. And just like before, we've got 3 rules, 1 for current, 1 for resistance, and 1 for potential difference. Let's start with current. When the current goes through a parallel circuit, this is the direction of conventional current we're going, so it's not the actual way the electrons are going, but don't worry about that just now. Let's say we have 10 amps leaves the cell. And it gets to this point here, this branch here, and it either goes that way or it goes that way. And what happens is, at this point here, the current splits. And a percentage or a portion of the 10 amps goes through branch 1. And a proportion of the current goes through branch 2. And let's say R1 is equal to 10 ohms and R2 is equal to 10 ohms. They're both the same. In which case, 5 amps would go this way and 5 amps would go that way, because 10 split into 2 is 5. And guess what happens when I get to this point here? And the total current goes back to 10 amps again. So for the current, our first rule is that the IT, the total current, is equal to I1 plus I2. And it goes back to being the total current again. So this is it as it leaves the cell. That's it in the branches. And this is it as it goes back to the cell. Or supply, whatever we're using there. The second thing we're interested in is resistance in a parallel circuit. Now, do you remember in a series circuit, the total resistance was equal just to all the resistors added together? And the effect had, so that the more resistors we had, more resistors, the more resistance of the circuit. More resistance of circuit. Well, that does not happen in a parallel circuit. The weird thing So the effect of resistors in parallel is to decrease the resistance of the circuit. And what that has the effect of is increasing the current. So it's the exact opposite of what happens in a series circuit. And there is a formula for remembering resistors in parallel, but you don't have to use it, so don't write this down. But there is a formula, so when you get into sixth form, into IB or A level or whatever you choose to do, then you'll learn that formula. But right now, let's forget all about it. All you need to know about resistors in parallel is that as you add resistors, the resistance of the circuit decreases and it increases the current. The final quantity we're interested in is potential difference, or voltage. Let's say that this circuit has a supply voltage of 12 volts. This branch 1, gets 12 volts. And branch 2 gets 12 volts. Each branch in a parallel circuit gets the same amount of volts as the supply voltage. VT equals V1 equals V2 equals VT. Each branch gets the same amount of voltage as the supply voltage, which is kind of cool. Just like with parallel circuits, there is a ratio sum that you can do to make things easier. And we're going to go back to thinking about current in a parallel circuit. Remember earlier I told you that the current gets to a branch and it splits up and either goes to branch 1 or 2. Well, the amount of current that goes into each branch really depends on the resistor in each branch. Well, as before, if they're both the same resistance, so if that's 10 ohms and that's 10 ohms, then the current would split equally. 5 amps and 5 amps would go that way. However, let's say we've got 12 amps going in here, and let's say that this is 100 ohms and this is 50 ohms. If I was a current, I'd probably want to go through branch 1 because it would be easier, there's less resistance. But some would still go through R2 as well. Twice the amount of current would go through here because this is half the resistance of that one. So what we'd have on this branch is we'd have I1 equals 8 amps. And down here on branch 2, what we'd have is I2 equals 4 amps. And that's because the R2 is twice the amount of R1, so it gets half the amount of current. So the resistance in each branch will determine how much current passes through each branch. Now you can use V equals IR to work these things out with a formula, but if you're particularly mathematically minded, then this ratio idea makes things a bit simpler. Let's head to your revision note template now, and in the common diagrams section, add a series circuit and a parallel circuit. Annotate each diagram with the relationships shown in the data booklet, and I've put them below here for you. Then head to question 14 and 15 in the knowledge questions that you can find downloaded below. Learning objective 13 is all to do with internal resistance. And we'll really dive into this concept here. I want to start with looking at something called supply voltage.
So if you're looking at a supply voltage, and this cell here has a supply voltage of 12 volts, what's actually happening is that each unit of charge, each coulomb of charge, is gaining 12 joules of energy. That's not to say that each electron gets 12 joules of energy, because in fact, in 1 unit of charge, 1 coulomb, there are actually 6.25 times 10 to the 18 electrons. So if we picture this, 6.25 times 10 to the 18 electrons, that group of electrons receives 12 joules of energy. We now know what electromotive force and potential difference is. It's important for us to understand what internal resistance is. What the voltage quoted on a cell or a power supply may be 1.5 or 10 volts or so on, but that's not the actual voltage that's supplied to the circuit, because inside this cell there are chemicals, and those chemicals pose a resistance to the current within it. Inside this power supply, there are little wires, and those little wires pose a resistance to the current flowing through it. Now, this resistance has to be accounted for in calculations, and if we look at a circuit diagram now, before we discovered the concept of internal resistance, we used to simply have this cell circuit diagram and then our components. But now we need to say, well, actually, our power supply has a small resistor within it. So we can have what you might often see is a sort of outline of a cell or a battery, and then the EMF supply within it, where the energy is supplied, and a small resistor shown within inside it. This small resistor leads to a term called lost volts. Let's read through this. When a current flows through the circuit, so the battery here is producing energy and it's giving energy to the electrons. Those electrons are flowing through the circuit, through the external resistor, background here, through the internal resistance and back to the cell where it's going to pick up more energy. So when a current flows through the circuit, the charge will transfer some of its electrical energy to the internal resistor. So when a current goes through this internal resistor, it's going to take some of the voltage, basically. It's going to take some of the potential difference. And this voltage that's taken is not going to be able to be used up here. So that's lost volts. You can't use that. And we can find out the value of those lost volts, V, by using I, the current through the circuit, times R, which is the value of the internal resistor. Say this gives out 10 volts, and this internal resistance takes up 1 volt. That means that there's only 9 volts left for the rest of the components using the circuit. So the potential difference across the terminals of the power supply, and across the terminals I mean between here and here, will be less than the EMF of the supply, because the voltage will be lost in the internal resistance. So we can make up an equation that says V, which is the terminal potential difference, is equal to E, which is the energy going into the system, minus the lost volts lost in the internal resistor, which also equals IR. And that's born from the idea of the conservation of energy. Energy must be conserved within this circuit. So as the charge goes around the circuit, the sum of EMFs must equal the sum of potential differences. So that the total energy into the system is E. Some of the charges lose energy at the terminal potential difference, and they lose energy in the internal resistor. And what we're left with is this generic equation for internal resistance.
Let's get some stuff written down in your revision notes now. In the common diagrams section, draw a circuit with the internal resistance highlighted within it. So that would be the diagram that was in the previous slide. Write down the equation for internal resistance
And then open up the knowledge questions below and complete questions 16 to 18.